Now, what will be the torque on a dipole which placed in external electric field? This is our external electric field. See, it is shown by parallel lines. Parallel lines all are in equidistance. So, suppose the dipoles are made of two charges, which is minus q, and this is plus q is at this place. We know that force on a charge is equal to electric force on electric charge will be q into E. So here plus on the plus q charges, our electric field will be in the direction of the electric field, which is QE. And the force on the minus q will be just opposite of the electric field along this one. So this is minus QE. These two charges, since these two charges are equal and opposite, these two charges are equal in magnitudes. These two electric force are equal in magnitude, but in opposite direction. Plus QE along right hand side and minus QE along left hand side. So they make a couple. They make a couple. Couple means moment of a force. So they can rotate the dipole in the direction of the electric fields. So they can rotate along this one. This is dipole minus q to plus q. It can rotate along this one. Suppose if the distance between minus q and plus q is twice a, this is twice a. Now the dipole axis goes from minus q to plus q. Angle and the angle in the direction of E is theta. So now we know that torque is equal to force into perpendicular distance between these two forces. That the perpendicular distance here minus QE along this one plus QE along this one. The normal distance between them is BC. Force multiplied perpendicular distance between these two forces. Now torque generally represented by tau. So here force is equal to in magnitude QE, and the distance between these two equal forces, that the equal forces with the opposite signs. One is along this one, another is along this one. The distance between them will be BC. Now just multiplied by BC. From this triangle, sine theta comes out BC divided by hypotenuse. Our hypotenuse is AB. Now the length of AB is twice A. Now therefore it becomes BC divided by twice A. So now from BC is equal to twice A sine theta. Now the value becomes QE twice A sine theta. Also we know that the dipole moment of this system is equal to charge into twice A. Now it becomes twice A q. Twice A q will be the dipole moment. Now if all these place at equal distance, it comes out twice A q multiplied E into sine theta. Now this becomes twice A q will be E sine theta. Now our torque, which can rotate the dipoles in the direction of the electric field. We can say that the torque has a tendency to rotate the system clockwise direction in the direction of the minimum potential energy. So minimum potential energy of the systems will be in the direction of E. Now the torque now becomes vector format P cross E. P cross E will be in the vector format. The dipole moment has the directions from minus q to plus q along this one, and electric field is along this one. Now by the right hand palm rules, the directions comes out. The directions of this, if you turns all your finger right hand along the direction of first vector and turns your all fingers in the directions of the electric field, the thumbs will indicate the directions of P cross E. Now the P cross E directions has in the normal to this, inward normal on this field. Now the SI unit, SI unit will be, P has the value charge, that is coulomb into meter. Coulomb into meter, electric fields. You know, electric field is equal to force divided by Q. Now it comes on Newton divided by Coulomb. Now the unit becomes Newton into meter. The torque of this one. Therefore our torque is equal to P sin theta. Now the maximum torque, T maximum will be when the angle between dipole moment and electric field is equal to 90 degree. So P sin 90. Sin 90 has the value. So this is our maximum value. The electric field has the tendency, the torque has the tendency to place the dipoles in the minimum potential energy. The dipoles will be aligned in the direction of minimum potential energy. Minimum potential energy will be your stable equilibrium, or I can say that it is stable equilibrium. Now our next topic will be potential energy of a dipoles in an external electric field. So dipoles, if the dipoles align, it means that the stable equilibrium position will be when the dipoles align along this one, minus Q and plus Q, and your electric field is along this one. So dipole moment has the value from minus Q to plus Q, and electric field has the same direction. So when the dipole moment align with the electric field, it will be your stable equilibrium position, or I can say that minimum potential energy.